if you were to take a standard, normal-sized marshmallow, just a regular marshmallow you put in your hot cocoa,
Right.
and you were to drop it onto the surface of a neutron star, well, the resulting impact would release approximately the exact same amount of energy as a 3-megaton nuclear warhead detonating.
Yeah, that is an incredibly sobering visualization, and it is completely accurate to the physics.
I mean, it's just wild to think about. Today, for you, the listener, we are officially abandoning the comforting idea of stars as these, peaceful, glowing cosmic campfires.
Oh, absolutely. We are way past the campfire stage.
Yeah, we are looking at the ashes. We are doing a deep dive into the ultra-dense, city-sized corpses that get left behind when a massive star loses a roughly billion-year war against gravity.
And it's a war. Gravity always wins eventually.
Exactly. So we've got this stack of deeply complex, frankly mind-bending sources today, and the mission for this deep dive is to go straight to the absolute limits of the universe.
Right, to unpack the physics of neutron stars.
Exactly. We are going to explore what they actually are, how unfathomably extreme their physical state gets, the cosmic cataclysms they trigger, and honestly, what they reveal about the fundamental nature of matter itself.
Well, before we take a single step further into these sources, I think we need to establish a very strict, uncompromising baseline for this deep dive.
Okay, lay on us.
Because as we go through these physical mechanisms, as we discuss scales and densities that sound completely fabricated, you have to keep one absolute rule in mind.
Right.
These are real objects. We are not talking about theoretical math problems on a chalkboard.
Right, this isn't sci-fi.
Exactly. We are not discussing abstract thought experiments. We are talking about physical bodies that exist out there in the vacuum right now.
Which is the craziest part.
A neutron star is roughly 20 kilometers across, basically the size of a city, yet certain models suggest they contain more mass than our entire sun.
A whole sun crammed into a city.
Right. They are the densest objects in the universe that we can actually observe, and they are, without question, stranger than anything in science fiction.
Because in science fiction, I mean, the writer eventually hits a wall where they say, okay, that's too ridiculous, the audience won't buy it.
Yeah, you have to maintain suspension of disbelief.
Right. But the universe clearly does not care if we buy it or not. The physics just happen.
Mm-hmm.
And that marshmallow example perfectly illustrates it.
It really does. The gravity is so immense that even a marshmallow or a feather falling to the surface accelerates to a significant fraction of the speed of light.
It's just insane.
The kinetic energy of the impact alone creates a nuclear-level explosion.
Okay, let's unpack this, because I want to lay out exactly how a structural anomaly like that is even born. It's basically the ultimate story of collapse, right?
Yes. It requires us to look at the very end of a massive star's life cycle.
Right. So let's bypass the early stuff. I know you, the listener, probably understand basic stellar nucleosynthesis.
The basics.
We know a star is this massive balancing act, hydrostatic equilibrium. You have gravity crushing inward and nuclear fusion pushing outward.
A very delicate balance that lasts for millions of years.
Exactly. And we know a massive star fuses hydrogen, then helium, then carbon, oxygen, all the way down the periodic table until it hits this terminal wall, the iron core.
Right, because fusing iron requires more energy than it releases. So the outward pressure of the star simply ceases to exist.
The fusion engine just turns off.
It just stops. And this is where the physics gets spectacularly violent. In a matter of seconds, the core of the star reaches a temperature so high that the thermal photons, the light itself, become energetic enough to physically smash the iron nuclei apart.
Photodisintegration.
Exactly.
Millions of years of careful atomic fusion just undone by gamma rays in a fraction of a second.
It's incredibly fast. And when those nuclei are shattered into free protons and neutrons, the density skyrockets.
Right.
At this point, the only thing holding the core up against the crushing weight of the entire star is something called electron degeneracy pressure.
Okay, explain that for us.
It is a quantum mechanical rule, the Pauli exclusion principle, which basically dictates that two electrons cannot occupy the exact same quantum state at the exact same time.
So they literally push back.
Right. The electrons physically refuse to be squeezed any closer together.
But gravity doesn't care about quantum mechanical rules.
Not at this scale, no.
No.
The mass of the star is so overwhelming that gravity actually overpowers the Pauli exclusion principle.
Which is mind-blowing.
The pressure is so incomprehensibly high that the electrons are violently forced inside the protons.
Wow.
Through a process called inverse beta decay, the protons and electrons merge, neutralizing their charges, and they transform into neutrons and neutrinos.
And because neutrinos, barely interact with normal matter, they just instantly flee the scene.
They do. They take almost all of the energy of the collapse with them, flying out into the universe.
Roughly 99% of the supernova's total energy, right?
Approximately, yes. Carrying it all away. And what is left behind, when the outer layers of the star crash down, bounce off this new ultra-dense core, and explode outward, is the neutron star. A sphere made almost entirely of neutrons, packed shoulder to shoulder with absolutely zero empty space between them.
Which brings us to the physical reality of the density. And, we have to do the teaspoon analogy from our sources.
It's mandatory.
It is. But I want to explicitly explain why it works. You, the listener, look at the chair you're sitting on or your own hand.
Right, just normal matter.
Normal matter is almost entirely a vacuum. The nucleus is tiny and the electron cloud is huge. But in a neutron star, gravity has entirely evicted the vacuum.
The empty space is just gone.
Completely gone. So if you imagine scooping up one single standard kitchen teaspoon of this neutron star material, you aren't just scooping up matter.
No.
You are scooping up billions of collapsed atomic nuclei crammed into a sugar cube-sized space.
And according to the calculations in our sources, that single teaspoon would weigh approximately 1 billion tons.
1 billion tons. Let that sink in.
It's hard to even visualize.
It is. If you took the entire mass of Mount Everest,
Yeah.
every rock, every glacier, the entire sheer continental weight of it, and somehow compacted it into a spoon you use for soup,
Right.
that is what we are dealing with. Or the sources offer another visualization, which I think is even crazier.
The Eiffel Towers.
Yes.
Or
Roughly 100,000 Eiffel Towers. Picture the massive iron latticework of just one Eiffel Tower. Now, imagine roughly 100,000 of them crammed into a single cubic centimeter by some giant cosmic compactor.
See, when I look at the exact same data, the exact same physics, I actually find it beautifully elegant.
Elegant, are you kidding? I find it existentially terrifying.
Terrifying. Why?
Because there is something profoundly unsettling about the crushing reality of
Doubles.
gravity winning. So absolutely.
It's just the laws of physics playing out.
But all structure, all chemistry, all the empty space that makes matter interact and exist in a recognizable way, it's just obliterated.
Whoa.
It feels like a violent end to existence. How is 100,000 crushed Eiffel Towers beautiful?
Because it is nature's ultimate packaging.
Ultimate packaging.
Yes, it is matter reduced to its most fundamental, mathematically pure state.
Okay, I guess I see that.
The universe strips away all the excess, all the complex chemical interactions that make things messy and unpredictable.
Right.
And it leaves behind this pristine, ultra-dense sphere of degenerate matter. It is physics operating at peak efficiency. It's not a violent end, it's a profound state of order.
Well, speaking of that profound order, the January 2026 data in our sources is fascinating because it digs into the actual internal structure of that order.
The structural simulations.
Yeah. We're getting past the old idea that it's just a uniform ball of neutrons. The new models are suggesting a distinct crystalline crust.
Right.
And maybe an ocean of superfluid neutrons beneath that. And then this is the best part, this bizarre transition zone they call nuclear pasta.
Yes, the nuclear pasta phase.
Where the neutrons form shapes like tubes and sheets, literally spaghetti and lasagna formations of nuclear matter right before you hit the core. It's wild.
Okay, that is all incredibly compelling, but I have to play devil's advocate here and step in.
Go for it.
I am looking at these January 2026 structural simulations of nuclear pasta and superfluid oceans, but let's be intellectually rigorous. But how do we actually know that?
That's a fair question.
Because we cannot send a probe into a neutron star.
No, obviously not.
We certainly cannot scoop up that teaspoon of matter to check its crystalline structure. The gravity is billions of times stronger than on Earth. Any physical instrument would be smeared into a single layer of atoms before it even touched the surface.
You would just be atomized.
So how much of this is observational fact and how much is just math on a chalkboard?
That is the perfect skeptical pushback. And you are right to clarify that. The sources strictly frame this as certain models suggest.
Right. It's conditional.
Exactly.
Yeah.
We know this through deeply complex mathematical extrapolations of how the strong nuclear force should behave under pressures we physically cannot replicate in any laboratory on Earth.
We don't have the tools to test it directly.
No, yeah. We observe how the star cools over time by looking at X-ray emissions. We observe its mass-radius relationship, and then certain researchers run massive supercomputer simulations.
To try match the data.
Exactly. They run these simulations to guess what internal structure perfectly matches those external observations.
So it is highly educated deduction, but our knowledge fundamentally relies on models that are still conditional.
Spot on. We are piecing together the inside based on how the outside behaves, which actually provides a perfectly logical transition into the next phase of our sources.
Right, because motion is a huge part of this.
Huge. Because one of the most vital ways we study these objects is by observing what happens to them mechanically when they collapse.
Yes, the rotation.
When you take the rotating core of a massive star and you shrink it from millions of kilometers across down to an approximately 20-kilometer sphere,
Right.
you are forced to deal with the conservation of angular momentum.
Right. It's the collapsing, rotating fluid dynamics. It's like the classic ice skater analogy.
Just pulling their arms in.
Exactly. As the radius decreases, the rotational velocity must increase to conserve momentum. But it is not just the physical matter that gets compressed. It is the magnetic field lines.
Yes. Let's unpack the mechanism of a pulsar.
When the star collapses, its original magnetic field is essentially frozen into the highly conductive fluid of the dying star.
Okay.
As the star shrinks down to city size, those magnetic field lines are squeezed together with it, amplifying the magnetic field to roughly 1 trillion times the strength of Earth's.
1 trillion times.
You now have a hyperdense, hypermagnetic sphere spinning frantically in the vacuum of space.
And the discovery of these objects is frankly one of the greatest observational stories in modern science. The sources take us back to 1967.
A classic moment in astronomy.
Astronomers were scanning the sky, and they detected a radio signal. But it wasn't the chaotic, random static you usually get from space.
No, it was entirely different.
It was a perfect, rhythmic pulse arriving approximately every 1.3 seconds. Tick, tick, tick.
And you have to put yourself in the mindset of an astrophysicist in the 1960s. You are listening to the messy, turbulent noise of the cosmos, and suddenly you hear a perfect metronome.
They initially named the signal LGM-1.
Yes, Little Green Men 1.
Because their first genuine thought was that it might be an alien beacon.
And honestly, it was a mathematically sound hypothesis at the time.
Was it really?
It was. They analyzed the dispersion measure of the signal, how much the low-frequency radio waves lagged behind the high-frequency ones, which proved the signal was coming from far outside our solar system.
Okay.
And what natural, unguided process in the universe could possibly keep time that perfectly across interstellar distances?
But as the sources note, it wasn't aliens. It was a pulsar. And I want to get away from the standard textbook analogy here, because people always compare a pulsar to a lighthouse sweeping a beam of light across the ocean.
The lighthouse analogy is a bit too serene.
Way too serene. The physics are so much more violent than a lighthouse. A pulsar is actually a massive, naturally occurring particle accelerator, isn't it?
That is a vastly superior way to describe it, yes. The magnetic field lines at the poles of the neutron star are whipping through the vacuum of space at a significant fraction of the speed of light.
Because it's spinning so fast.
Exactly. This creates an induced electric field so powerful that it literally tears charged particles, electrons and positrons, right off the solid surface of the neutron star.
It rips the surface apart just through the sheer force of the spinning magnetic field.
Yes, and it accelerates those particles along the magnetic field lines out into space. As these particles accelerate, they emit what is called synchrotron radiation.
Okay, and that is what?
Highly focused beams of radio waves and gamma rays shooting out of the magnetic poles.
And because the magnetic poles don't perfectly align with the star's axis of rotation, kind of like how Earth's magnetic north isn't exactly at the North Pole,
Right.
those beams sweep across the sky as the star spins. If Earth happens to sit directly in the line of sight of that sweeping beam, our radio telescopes detect a sharp pulse of radiation every single time the star completes a rotation.
Which brings us to the extremes of that rotation. The 1967 Discovery was spinning roughly once a second.
Which already sounds fast for a star.
It does. But the sources highlight the millisecond pulsars. These are older neutron stars that have managed to lock into a binary orbit with a companion star, and they slowly siphon off gas from their neighbor.
Like a cosmic parasite.
Essentially, yes.
Yeah.
As that gas falls onto the neutron star, it acts like a cosmic whip, spinning the star up faster and faster over millions of years.
Until they reach rotational speeds that are genuinely hard to visualize. We are talking about millisecond pulsars spinning approximately 700 times per second.
Let's contextualize that. Imagine standing in a city, say, Chicago.
Okay, I'm in Chicago.
Now imagine the entire metropolitan area of Chicago spinning on an axis roughly 700 times every single second.
Okay, wait. I have an insight here that I want to test against the physics.
Go for it.
Because if we have a sphere with roughly a 10-kilometer radius and it is spinning 700 times a second, I did the rough math on this earlier, the equator of that star must be moving at something like 15 to 20% the speed of light.
That is correct.
Doesn't relativity start aggressively warping the emission pulses we see?
That is an excellent observation, and yes, it absolutely does. Because the equator is moving at relativistic speeds, we observe effects like Doppler boosting.
What does that look like?
The light emitted from the side of the star spinning toward us is significantly brighter and more energetic than the light from the side spinning away. The pulses are time-dilated.
Wow.
And the gravity of the star itself is so immense that it bends the light from the far side over the horizon, meaning we can sometimes see more than half of the star's surface at once.
It is basically a playground for Einstein's theories of relativity.
It really is. And despite all that relativistic chaos, they are so stable that their pulses arrive with a regularity more precise than the best atomic clocks on Earth.
Which is exactly why astronomers are currently using them as a galaxy-sized laboratory.
Yes. This introduces the concept of pulsar timing arrays.
Right. Because we have this network of millisecond pulsars spread across the Milky Way, all ticking away perfectly. Certain studies suggest we can use them to detect gravitational waves.
Exactly.
Because if a massive gravitational wave, a literal stretching and squeezing of space-time caused by supermassive black holes colliding in another galaxy,
right.
If that wave rolls through our neighborhood, it fundamentally alters the distance between Earth and those pulsars.
The physical space itself stretches. So, for a tiny fraction of a moment, the pulses from those perfectly timed pulsars will arrive just a tiny bit early or a tiny bit late.
It's just brilliant.
By measuring those microscopic nanosecond delays across a whole network of pulsars, certain researchers can essentially use dead spinning stars as a galactic-scale seismograph.
Okay, I have to step in and push back on the structural physics here.
Okay, where's the issue?
Because I understand the timing array. That makes sense.
Yeah.
But how do we actually know that the object itself is stable?
Stable in what way?
You are telling me we have a city-sized object, heavier than the sun, with an equator moving at 20% the speed of light. How does it not just violently fly apart? If I spin a wet tennis ball, the water flies off. The centrifugal force should tear it to shreds. How do we actually know how it maintains hydrostatic equilibrium?
It is a very delicate balance existing right on a razor's edge.
Okay.
The reason a millisecond pulsar doesn't tear itself apart is purely because the inward pull of that billion-ton per teaspoon gravity is still barely stronger than the outward centrifugal force.
So gravity is just holding on for dear life.
Exactly. It comes down to the Roche limit and the tensile strength of the star's crust. However, our understanding of the stability is entirely conditional. Current physical models of the nuclear strong force suggest that if a neutron star were to spin just a little bit faster, say, approximately 1,200 times a second, gravity would no longer be sufficient.
Breaking point.
Yes, the centrifugal force would overcome the binding energy and the star would fly apart. They are operating at the absolute maximum speed limit allowed by the laws of physics.
The absolute maximum speed limit, which perfectly tees up the next extreme in our sources.
Oh, yes.
Because we've established the unfathomable density. We've established the relativistic spin. Now, I want you, the listener, to imagine what happens when the magnetic field of this dense, spinning fluid doesn't just act like a particle accelerator.
Right.
What happens when it becomes the dominant force dictating the star's entire behavior? We move from pulsars to magnetars.
The most intensely magnetic objects currently known to exist in the universe.
What physically dictates whether a newborn neutron star becomes a standard pulsar or mutates into a magnetar? What's the difference?
It is generally believed to come down to a highly specific dynamo effect in the first few seconds of the star's life.
The first few seconds, that's it.
Just the very beginning. When the core collapses, if the internal convection, the boiling, churning movement of the ultra-dense neutron fluid happens to synchronize perfectly with the star's rotation, it acts like a massive cosmic electromagnet.
An alpha-omega dynamo.
Yes. This dynamo rapidly amplifies the magnetic field before the star's crust fully solidifies. A regular pulsar has a magnetic field roughly millions of times stronger than Earth's.
Which is already huge.
But certain models suggest a magnetar's magnetic field is amplified to roughly 1,000,000,000,000 times stronger than Earth's.
Okay, let's try to ground that number in reality.
Yeah.
Because the human brain, frankly, is not equipped to process the word trillion in terms of force.
It's just a word until you put it in context.
Right. Earth's magnetic field is strong enough to move a compass needle. It creates the auroras. It shields our atmosphere from the solar wind.
It's vital for our survival.
Now, take that exact force and multiply by roughly 1,000,000,000,000.
Yeah.
If one of these magnetars were somehow placed near Earth, what are the physical consequences?
Well, let's put the magnetar at a seemingly safe distance. Let's place it at the distance of the moon, roughly 240,000 miles away.
Okay. From that distance, the moon's gravity gives us tides, but its physical presence doesn't alter our daily lives.
Right. 250,000 miles seems like a good buffer.
It seems perfectly safe.
It is not.
No.
Not even close. If Magnetar were sitting at the distance of the moon, its magnetic field is so profoundly dominant that it would reach across the void of space and fundamentally rewrite the atomic structure of your body here on Earth.
Wait, what? It would affect the quantum mechanics of my atoms from 250,000 miles away.
Yes. To understand why, we have to look at how an atom is built. You have the nucleus in the center and the electron cloud orbiting it, held in place by the Coulomb force.
The electromagnetic attraction between the positive nucleus and the negative electrons.
Exactly. But a magnetar's magnetic field is so overwhelming that it completely dominates the Coulomb force.
Okay.
It would physically stretch and distort the electron clouds in your body, forcing them out of their spherical shapes and compressing them into long, incredibly thin tubes known as Landau cylinders.
So the actual physical shape of the atom changes.
Yes.
But all of chemistry, the way carbon bonds with oxygen, the way DNA spirals, the way proteins fold in our cells, is entirely dependent on the specific three-dimensional shape of those electron clouds.
Exactly. So if the electron clouds are forced into Landau cylinders, chemistry simply ceases to function.
Oh, wow.
The molecular bonds in your body would instantly dissolve. You wouldn't be crushed. You would simply disintegrate at a subatomic level into a cloud of unbonded atoms.
What's because the magnetic field from the moon overpowered the chemical forces holding my molecules together?
Yes.
That is simultaneously the most horrifying and fascinating thing we have covered so far.
It's extreme physics.
And here is where the sources get extremely exciting. Because for a long time, magnetars were these elusive, terrifying ghosts,
Right. We only saw them long after they were formed.
But the research from July 2026 highlights an observational breakthrough.
The chirping signal.
Yes. Certain astronomers recently detected a distinct chirping signal in gravitational waves from a distant supernova, which revealed the actual birth of one of these extremely magnetic objects.
A chirping signal in a newly formed supernova remnant. That is a highly specific signature.
What does it mean?
It strongly suggests they were detecting the rapid spin-down or magnetic braking of the newborn magnetar as its immense magnetic field interacted with the expanding cloud of stellar debris.
Right. It's like throwing a massive hyperspinning magnet into a cloud of conductive plasma. The drag is going to be immense.
Very immense.
But how do we actually know that this chirp translates to a magnetic field 1,000,000,000,000 times stronger than Earth's? How can certain researchers make that claim just from a changing frequency?
That's a great question. It comes down to calculating the energy budget. We observe the spin rate dropping precipitously. We know the mass of the object. Therefore, we can calculate exactly how much rotational energy is being lost per second.
Okay, the mass dictates the energy loss.
Right. And the only physical mechanism capable of bleeding off that much angular momentum that quickly is a magnetic field of magnetar-level proportions, acting as a brake against the surrounding ejecta.
So the math simply doesn't balance without a roughly trillion Gauss magnetic field.
Exactly. It has to be that strong.
And that magnetic field is under immense stress. It's not just a static aura around the star.
No, not at all.
Because the crust of the magnetar is a rigid lattice of atomic nuclei, and the magnetic field lines are locked into that crust.
Yes, imagine a ball of incredibly stiff metal wrapped tightly in billions of ultra-strong rubber bands, all twisted and fighting against each other.
That's a great visual.
As the magnetic field slowly decays or shifts to find a lower energy state, it puts immense physical tension on the crust.
Until the tensile strength of the crust fails.
And when it fails, the crust cracks. A starquake.
But a starquake on a magnetar isn't just a seismic event like an earthquake here.
No, the scale is completely different.
Because the crust is tied to the magnetic field, a crack in the crust causes the magnetic field lines to suddenly snap and reconnect.
And the energy release is staggering.
Unimaginable.
Certain studies suggest that these magnetar starquakes are believed to power some of the brightest, most violent short-duration gamma-ray bursts in the universe.
Wow.
In approximately a tenth of a second, a cracking magnetar crust can release more energy than our sun will output in its entire 10 billion-year lifespan.
It is the universe's ultimate flashbulb.
It is. But adhering to our rule of rigorous framing, certain studies suggest this connection. The exact mechanisms linking the seismic shearing of a neutron star crust to the generation of a superluminous gamma-ray flare involve deeply complex plasma physics that we are still modeling.
Right, it's not totally confirmed.
It is the leading candidate to explain these cosmic explosions, but it remains conditional.
Which perfectly sets the stage for the most violent event in our sources.
Yes.
Because we have spent, half an hour establishing a single neutron star as a limit-breaking extreme of nature.
The density, the spin, the magnetism.
Right. The billion-ton density, the relativistic spin, the atom-dissolving magnetism. But now we have to look at the physical consequences of binary systems.
Right.
What happens when two of these absolute extremes lock into a decaying orbit and collide?
You get a kilonova.
A kilonova.
And from the perspective of human existence, this is arguably the most profoundly important event in the entire cosmos.
That's a huge claim. Let's walk the listener through the mechanics of this collision.
Yeah.
Because it's not just two billiard balls knocking into each other in space.
No, it's a gravitational death spiral.
Right.
It begins with gravitational radiation. As these two city-sized hyperdense masses orbit each other, they churn the fabric of space-time, emitting gravitational waves that carry energy away from the system.
Okay, so they're losing energy constantly.
Yes. As they lose energy, their orbit shrinks. They spiral closer and closer, spinning faster and faster. In the final milliseconds, they are orbiting each other hundreds of times per second.
And the tidal forces must be astronomical, because the gravity on the surface of a neutron star is immense. But when another neutron star gets within a few dozen kilometers, their gravities start fighting.
The tidal shearing is so extreme that the rigid crusts of the stars actually begin to fracture and tear apart before the objects even physically touch.
They just rip each other apart.
And when they finally merge, the resulting explosion is a kilonova. For a brief window of time, this singular collision produces more energy than hundreds of billions of normal stars combined.
It literally outshines its entire host galaxy.
Easily.
But the light show isn't why it matters to you, the listener. The reason we are exploring this is because of what is forged in that explosion.
Yes, the chemistry.
I want you to look at your surroundings. Look at the gold ring on your finger. Think about the silver in your electronics, the platinum in catalytic converter, or the uranium used in nuclear reactors.
For decades, textbooks taught that all heavy elements were made in regular supernovae.
But the advanced models eventually showed that the math of a standard supernova doesn't work for the heaviest elements, right?
Exactly. A normal supernova simply doesn't have a high enough density of free neutrons, and the intense neutrino winds in a supernova actually destroy neutrons, preventing the rapid buildup of the heaviest atomic nuclei.
So to make gold, you need a highly specific environment.
Very specific.
You need an environment where an atomic nucleus can gorge itself on free neutrons incredibly fast, faster than the nucleus can radioactively decay and fall apart.
Precisely. It is called the rapid neutron capture process, or the R process.
MAR process.
And a neutron-star collision provides the absolute perfect, purely neutron-rich environment for this. When these two billion-ton per teaspoon objects smash together, the sheer kinetic violence ejects a small percentage of their mass out into space.
It is literal cosmic shrapnel.
Yes. And because that shrapnel is made of pure neutrons suddenly freed from the crushing gravity of the star, it rapidly decompresses.
And then what happens?
The neutrons start clumping together, furiously building up from lighter seed nuclei into the heaviest elements on the periodic table in a matter of seconds.
Seconds. Which is why certain models suggest that the vast majority of heavy elements, including gold, platinum, and uranium, were forged exclusively in neutron star collisions.
It is a remarkable synthesis of astrophysics and everyday chemistry.
I just think it's so cool. The gold on your finger is literal debris from a space-time-bending collision of dead stars that happened billions of years ago.
It really is.
It genuinely changes how you look at a wedding ring. It's not just a rare metal pulled from the dirt. It's the physical scar of a cosmic catastrophe.
It is, and the observational astronomy surrounding Kilonova is currently accelerating at a staggering pace. Our sources present two highly significant recent detections that expand our understanding of these mergers.
Yes, let's look at the March 2026 data. This one is genuinely chaotic.
It is very unusual.
Certain researchers recently detected a collision in an unusual, elongated, highly eccentric orbit.
Which is an incredible anomaly.
Why is that anomalous?
As we discussed earlier, gravitational waves bleed orbital energy away, which acts as a dampening mechanism. This typically circularizes the orbit over millions of years.
Oh, I see.
By the time a binary pair finally merges, they should be in a nearly perfect, tight, circular orbit.
Right. So to detect a collision happening from an elongated oval orbit means something violently disrupted them right before the merger.
Yes, it suggests a deeply chaotic dynamical history. It could be the Kozai-Lidov mechanism.
What's that?
It's where a massive third body, like a black hole or a third star in a tertiary system, gravitationally perturbs the binary pair, forcing their orbit into a highly eccentric shape.
Okay. Or what else could it be?
Well, it could suggest a massive supernova kick, where a recent explosion physically shoved the system into an oval trajectory mere thousands of years before they collided.
Which proves these systems are far more dynamic than a simple, clean spiral.
Absolutely. And then we have the theoretical side catching up to the observations.
Right, the December 2025 data. This one focuses on the buildup. Recent simulations have provided the most detailed look yet at what happens in the final milliseconds before two neutron stars collide.
Specifically tracking the exact waveform of the gravitational ripples.
Yeah, these simulations are computationally grueling, but they are absolutely essential.
Very essential. When our laser interferometers on Earth detect a stretching of space-time, it is just a raw waveform. We need these hyper-detailed simulations to decode the signal.
So the simulations tell us what?
They tell us exactly how the gravitational wave changes frequency as the stars warp and scrunch each other. This allows us to determine their masses, their spin rates, and even the stiffness of their crusts just from the shape of the ripple.
Okay, I have to jump in here and play the skeptic again.
Please do.
Because I love the narrative, I love the idea of the R process and Kilonova acting as cosmic gold factories.
Yeah.
But I'm looking at these December 2025 simulations, and I'm looking at collisions happening 130 million light years away.
Right.
But how do we actually know that they make gold? We certainly can't send a probe to scoop up the shrapnel from that far away.
No, we cannot.
So how much of this gold factory is observational fact, and how much is just highly confident math?
It is a vital scientific question, and the answer lies entirely in spectroscopy.
Spectroscopy.
We cannot physically touch the debris, but we can analyze the spectra of the light emitted by the expanding kilonova cloud.
By reading the chemical fingerprint in the light.
Exactly. When a kilonova ejects that R-process shrapnel, the freshly forged heavy elements are intensely radioactive.
Okay.
As they rapidly decay, they emit thermal energy, causing the expanding cloud to glow. But heavy elements, specifically the lanthanides and actinides, have highly complex atomic structures with millions of electron transition lines.
What does that mean for the light we see?
This creates a very specific, broad opacity in the light curve, particularly absorbing blue light and emitting strongly in the red and infrared wavelengths.
So the kilonova actually changes color in a very specific way because of the heavy elements.
Yes. When certain astronomers analyzed the spectra from observed kilonovae, the light curves perfectly matched the theoretical models of radioactive decay for newly synthesized heavy elements. The broad, red-shifted infrared glow was undeniable evidence.
That was amazing.
However, you are right to enforce skepticism because we must admit our certainty is still developing. We have only observed a handful of these events in high detail.
Right.
While the models strongly suggest neutron-star collisions are the primary source, the exact ratio of how much gold is produced per event and whether other exotic mechanisms like collapsers might also contribute is still an active area of intense debate.
So we are confident in the basic mechanism, but the cosmic accounting is far from settled.
Exactly.
And that profound lingering uncertainty brings us to our final exploration.
The frontier.
Yes. We have spent an hour marveling at the destructive force, the relativistic speeds, the atom-warping magnetism, and the cosmic forging of elements. We know exactly what neutron stars do to the universe around them. But as we transition to the final section of our sources, we have to ground ourselves back in scientific humility. because for all our data, we still don't actually know what a neutron star truly is at its deepest core.
This is the ultimate frontier of astrophysics. It is where our math fundamentally breaks down.
Right.
In physics, it is referred to as the equation of state problem.
The equation of state problem. Let's make sure that concept is crystal clear. An equation of state is basically a mathematical formula that describes the physical state of matter under a specific set of conditions like pressure, density, and temperature.
That's right.
We have an equation of state for the water in the ocean. We know exactly how it behaves when it freezes or turns to steam.
Right. We have equations of state for the plasma inside our sun. We have them for the iron core of the Earth.
But when you try to calculate the equation of state for the exact center of a neutron star,
the math simply fails us. We do not have the physical framework to describe it.
it's just a blank spot.
The matter inside the inner core of a neutron star is at a pressure and density that we cannot recreate or even properly simulate in any particle accelerator on Earth.
Wow.
We know the outer crust is likely a rigid lattice. We are fairly confident the outer core is a superfluid sea of neutrons, but at the exact deep center.
The pressure is so incomprehensibly extreme that we literally do not know what the neutrons themselves do.
Do they just remain as incredibly packed neutrons? We don't know.
What are the other options?
Well, some models suggest the pressure is so high that the neutrons themselves crack open, breaking down into their constituent quantum parts, quarks, creating a theoretical quark-gluon plasma,
Oh, wow.
or a state of color superconductivity. Other models suggest the energy is high enough to spontaneously form exotic new particles called hyperons, which contain strange quarks.
Bizarre new phases of degenerate matter that we haven't even theorized yet.
We simply do not know. The environment is so extreme, it fundamentally breaks our current understanding of the strong nuclear force.
And that unknown is exactly what is driving the future of this field, as outlined in the final pieces of our sources.
Right, the observational tools.
We are constantly building new observational tools to try and gather enough data to solve that equation.
Yeah.
Look at the data expected from May 2026.
The new telescope.
Yes, the sources note that a new, highly advanced space telescope expected to launch later this year, designed for wide-field infrared surveys, may reveal millions of hidden, isolated neutron stars.
Millions of them. Which is crucial because right now we mostly find pulsars that are beaming radiation directly at us, or neutron stars in binary systems that are feeding on a companion.
But there should be hundreds of millions of cold, isolated neutron stars just drifting quietly through the Milky Way.
Yes. And by finding them through faint thermal emissions or gravitational microlensing, we vastly expand our census. More data points, more mass radius measurements give us a better chance to crack the equation of state.
And it's not just about building better hardware. It is about finding brilliant new ways to analyze the data we are already collecting. The sources point to a truly fascinating study from June 2026, where certain researchers applied advanced machine learning algorithms to analyze a highly controversial, mysterious gamma ray glow at the absolute center of the Milky Way.
Ah, the galactic sentinel gamma ray excess.
Yes. For years, this was one of the biggest mysteries in astrophysics. There is this diffuse, unexplained glow of high-energy gamma rays coming from the core of our galaxy.
And for a long time, many physicists hypothesized it was the Holy Grail, the signature of dark matter particles colliding and annihilating each other.
But the June 2026 machine learning analysis suggests a completely different and arguably more complex reality.
What did the AI find?
The AI was trained to distinguish between the perfectly smooth, diffuse emission you would expect from a dark matter cloud and the grainy, point source emission you would get from thousands of distinct, tiny objects.
Exactly. And the algorithm concluded that the glow is likely not dark matter at all, but rather the collective overlapping radiation from tens of thousands of ancient, previously undetected millisecond pulsars.
All huddled tightly in the gravitational well of the galactic core.
If we connect this to the bigger picture, it demonstrates how new technology, artificial intelligence parsing complex spatial distributions of photons, is actively peeling back the layers of the cosmos to reveal vast hidden populations of these extreme objects.
It really is a humbling realization.
It is.
Both of us can sit here and debate the staggering numbers. We can explain the billion-ton teaspoons, the relativistic dynamo effects, the atom-crushing magnetic fields, and the space-time-bending Kilonova collisions that forged the gold on Earth.
We can map the effects perfectly.
But at the end of the day, if you ask either of us, what is the exact physical state of matter at the absolute center of that star? We have to openly, transparently admit our uncertainty.
We do not have the definitive answer. The brightest minds and the most powerful supercomputers in physics do not have the definitive answer.
And that is exactly what makes astrophysics so compelling. The uncertainty is not a failure of our methods. It is an open invitation to push the boundaries of human knowledge further.
We are standing on the shore of an ocean of quantum gravity, and we're just beginning to map the depths.
We've journeyed from the violent collapse of a massive star to the perfect relativistic ticking of a pulsar, to the atomic warping dominance of a magnetar, to the cosmic forge of a kilonova.
If we pull all these disparate threads together, what we have explored today is a portrait of nature operating at its absolute, uncompromising maximum capacity.
The absolute peak.
The incomprehensible density, the sweeping radio beams, the explosions that outshine entire galaxies, they all stem from the simple, terrifying fact that gravity ultimately overpowered fusion and crushed atomic matter into its most fundamental, irreducible state.
It's beautiful and terrifying.
A neutron star isn't merely a dead star. It is the universe's ultimate extreme physics laboratory. It is the crucible where the heaviest elements in your body and your technology are born, and it is the precise metronome by which we can measure the literal ripples in the fabric of space-time itself.
And that brings us to the final, provocative thought I want to leave you, the listener, with today. Think about that equation of state problem we just discussed.
The ultimate unknown.
Think about how the deep core of this star physically breaks our mathematics. Neutron stars exist at the absolute razor-thin limit of what matter can physically be. They are the final boundary line between the physics we can partially understand and the total catastrophic collapse into a black hole where all physics as we know it ceases to exist.
The edge of reality.
They are the edge of reality. If we ever manage to figure out what is truly happening inside them, if we understood them completely, we might understand everything.